Okay, thanks. Thanks everyone for coming. It's nice to see you here. Today we have two very interesting talks. Let me introduce you. The first speaker is Ketan Rikame. He's a postdoctoral fellow at the Raman Research Institute in Bangalore in India, and he also is a member of the Indian X-ray polarimetry POLIX team. He contributed to the development of the deployment of the POLIX instrument and is actively involved in the analysis of the POLIX data. And his research interests include X-ray binary systems and X-ray polarimetry. And today he's going to talk us about flares and bursts during eclipses of X-ray binary systems, and also initial results from the Indian X-ray polarimeter. Thank you.
Thank you for coming for the seminar. I'm Ketan. I'm from Raman Research Institute, India, and I'll be talking about two separate topics. One is flares and bursts during eclipses of X-ray binary systems, and the other I'll briefly talk about the initial results that we have from Indian X-ray polarimeter. In the interest of time, I'll be talking very briefly about all these these topics, but I'll be very happy to elaborate it on further if you have any questions now, or I'll be here for the rest of the day. So let's start. So X-ray binary systems are two-star system where one star is a main sequence star and other star is a compact object, which can be a neutron star or a black hole candidate. And these two stars are gravitationally bound to each other. And from the main sequence star, there can be a matter accretion onto the compact object, either through stellar wind capture from the companion star or the Rauschelot overflow from the companion star. Based on the mass of the companion star, roughly we can classify these systems into two categories: high mass X-ray binary systems and low mass X-ray binary systems. High mass X-ray binary systems, the companion star is a very big giant star, and generally it has a very it is very much active. Stellar activity is there. Stellar wind is being thrown out, and that is gravitationally captured through by the the compact object. And in low mass X-ray binary systems, the companion star is less massive, and then when the Rauschelot of the companion star is filled up, then through Rauschelot overflow, the matter accretion happens near the compact object through matter accretion, and then through process like inverse Compton scattering or the black body. These objects emit X-rays, and this is the source of primary X-ray radiation from these objects. In today's talk, I'll be focusing on the not the primary radiation, but the another kind of radiation that is seen in the system called reprocessed emission. So basically, in these systems, once the X-ray radiation is generated at the near the compact object through the processes I mentioned, then that radiation can interact with the surrounding of the X-ray binary system, and that secondary radiation after interaction with the surrounding, we call it reprocessed emission, that contains the clues about the environment of the X-ray binary system, and that is what I'll be talking about in this talk. So in general, when we are looking at this system, the primary X-ray radiation is very dominant, and when you're looking at the overall radiation received from the systems, that is the dominant one, and we cannot see this reprocessed emission. But then several particular class of this X-ray binary system where the line of sight is such that the systems are so the companion star is eclipsing the compact object every time. So these are eclipsing X-ray binary system, and during the eclipses of such systems, the primary radiation is completely blocked, and all we see is the reprocessed emission, which contains the signature of interaction of that primary radiation with its surrounding. So we can study the comparison between this reprocessed emission and the primary radiation. That helps us understand what kind of ionization levels are present in the vicinity of in the circumbinary environment, and we can do a lot of more things. Our research group there has done extensive work on X-ray binaries. So previous to me, there were already studies about comparing this reprocessed emission with with out of eclipse emission, and that can help us understand at what what is the distribution of circumbinary material, what are the ionization level, etc. So as a next step to this work, I started looking at eclipse variability in this system. So these systems generally show a lot of variability, such as we can see flares due to increased mass accretion in high mass X-ray binary systems, or the low mass X-ray binary systems. The neutron star low mass X-ray binary systems show a particular class of variability called thermonuclear burst. And we tried to we did our search to look for variability in the eclipse, such variability in the eclipse of such systems. I'll come to it. What was the motivation for looking for something like that? So so the first part of this work was based on high mass X-ray binary systems. In high mass X-ray binary systems, flares can originate due to, like in high mass X-ray binary system, the main mechanism for mass accretion is the stellar wind capture from the companion star, and due to inhomogeneity in the winds and all, there can be accretion rate increase based on the capture of the stellar wind, and that can give rise to that can give rise to flares in high mass X-ray binary systems. So here we are seeing, like, if we're looking for some variability in the eclipse, we need to keep in mind that it is in eclipse, that it is eclipsed by the companion star. So we're not seeing the primary radiation. So what are the radiation we are seeing is through the interaction of its surroundings. So if you are seeing some variability, that is probably originating at the central compact object. The reprocessed emission is showing that variability. So it first gives us the very first constraint on the size of the reprocessing region, that it has to be greater than the size of the component object, that is. Otherwise, we cannot see that variability. And then later on, by comparing the eclipse, okay, so for this high mass X-ray binary systems, we did the systematic literature survey for like, can we find the such eclipse variability in such high mass X-ray binary systems, and we found that three systems, Vela X1, LMC-X4, and 4U1737, these three systems showed flares during the eclipses of such systems. So this is the representative of how these three systems are. Well, X1 and 4U1737 have a pretty extended orbits. LMC-X4 is a bit compact in that sense. 4U1700, there is a very interesting result came out of this work. 4U1737 is a very special type of high mass X-ray binary system, because its companion star is one of the most volatile and active companion star known for X-ray binary, known in high mass X-ray binary systems. So once we identified that there is eclipse variability seen in the systems, we identified those observations, and four of the observations, like two observations for 4U1737 and one each for Velaxano and for LM64, we found the eclipse flares in these systems. So we extracted the eclipse flares and eclipse non-flare data, and we compared the spectra, and we have done the detailed spectral analysis. I will not go into details of that. I'll just point out an interesting result that we have found in the system. So in 4U1737, the red one here is the eclipse flare spectrum, and the blue one here is the eclipse non-flare, or the region in eclipse where we did not see flare, that spectrum. So you can see the x-axis is the energy. At higher energies, there is a proportionate increase in the flux during the eclipse flare. However, in this low energy, this particular part, regardless of whether it's in flare or non-flare, that part, that soft X-ray emission does not change. So that indicates that that particular soft excess originates from a region which is not close to binary, the compact object in the X-ray binary. Because if it were, then with the increased accretion rate, we would see enhanced emission there also. So generally, soft excess is observed in high mass X-ray binary systems, and it is modeled with a black body, and it can be coming from the accretion disk or some kind of a structure around it. So we initially modeled it with a black body, but then having such a third black body, just like that in an X-ray binary system, is difficult to understand. But then such soft excess can originate through several other processes. One of the processes is thermal bremsstrahlung. Thermal bremsstrahlung can originate in the ionized wind of the companion star. However, generally in high mass X-ray binary system, the companion star is is most active in optical or UV energies. It is not known to emit in X-ray energies. But then, as I mentioned, 4U 1737 is a special system because its companion star is known to be the most volatile companion star. So we tried to model this observed soft axis in 4U 1737 with a thermal Bremsstrahlung model. Now, using the stellar wind parameters of 4U 1737 in literature, we also tried to estimate what would be the emission measure coming from the stellar wind of the 4U 1737 companion star and equated it with the thermal Bremsstrahlung emission that we got from the spectral analysis. And we indeed see that because 4U 1737 companion star is so volatile and its spectral wind parameters are like it is throwing out material at such a large accretion rate that even a thin shell of that stellar wind can produce the observed thermal Bremsstrahlung emission. So this was something interesting that we don't generally expect the companion star to emit in X-rays. But here in this case, we are seeing that it is one of the likely sources for observed non-varying soft axis in 4U 1737. Another thing that you can see is in the spectra of Vela X1 and 4U 1737, you can see a lot of emission lines that are there. This is a general characteristic of a reprocessed emission. Since primary radiation is blocked, the reprocessed emission is heightened is more pronounced in the eclipse duration, and particularly during that period, since the reprocessed emission that is generated because of the line emission, etc., is more prominently seen. Now here we can see that both eclipse flare and eclipse out of flare, which is like eclipse flare is shown in red and eclipse out of flare it's shown in the blue. There are multiple emission lines. So we measured the line widths of these lines, line energies of these lines, and our analysis indicates that for the most prominently detected lines, there is proportionate increase in the flux of these lines during the eclipse flare with respect to eclipse non-flare. So this also indicates that probably these lines originate near the X-ray binary systems, because if they were originating away from the X-ray binary systems, they would not show such proportionate increase. So I will not talk about other results from this work, but you can go to the paper or talk to me about what are the other. But these were the most significant things that came out. Then extending these study to low mass X-ray binary systems, we tried to look for, can we see eclipse variability in low mass X-ray binary systems as well? So as I said, like particular class of low mass X-ray binary system where compact object is a neutron star, we have a mass accretion through Rauschel-Bohr flow, and then the accreting material keeps on accumulating on the surface of the neutron star, and it starts to build a pressure, and with that temperature starts to increase, and a particular threshold is reached where the thermonuclear reaction is ignited. It can be characterized with such very characteristic flares where the sharp rise is the ignition, and then this exponential cooling time curve is seen. So these kind of a very particular flares are seen, called type 1 X-ray burst, in such low mass X-ray binary systems. So we looked for such eclipse flares in the data. So similar thorough archival data study we did for eclipsing low mass X-ray binary systems, and found that two low mass X-ray binary systems, EXO074866 and XTJ17102881, show variability such as eclipse flares in these systems. Now, this is archival RXC data, and doing the spectral analysis for this eclipse flare and eclipse burst and eclipse non-burst data was difficult. However, we came across something very interesting is that can be seen here itself. This particular duration is the eclipse out of eclipse duration and eclipse duration. We can see the eclipse of this system. But this burst has occurred right before the eclipse egress, and the same burst continues even in the out of eclipse region. So these very peculiar kind of burst can be very useful, because this is the same burst which is spanning in the out of eclipse as well as eclipse region. And if we can model the same burst with its physical parameters, that can help us understand the reprocessing fraction of the system. Reprocessing fraction is basically how much of the primary radiation is effectively converted to reprocessed emission that we can see. So when we looked at this archival data and we saw such peculiar bursts, we tried to look for those bursts. And EXO07486776, we saw 7 such eclipse transition bursts. And in XC7701281, we saw 1 such eclipse transition burst. So we thought of modeling these bursts so that we can get the reprocessing efficiency in these systems. So in XC7710281, this is the eclipse burst that I was talking about. So generally, these bursts are modeled with the fast rise exponential decay model, as shown here, the linear rise component and the exponential decay. So we added another scaling factor component. To scale the out of eclipse emission and eclipse emission. That will give us the idea about reprocessing fraction in this system. So for XTJ1710281, we were able to constrain this burst and get an estimate for the reprocessing fraction in this system. However, in EXO07486776, we were not able to fit this burst with a standard fast rise exponential decay profile with a scaling factor component. However, when we did some literature review on this source, then there have been reports of having presence of 2 decay components in the Fred profile of these systems. So, okay. Okay, I will wrap up. So since there is a presence of there is evidence for presence of 2 decay components in the modeling of this burst from this source, we also looked for archive, like whatever RXT data survey we had done. We also looked for some other out of eclipse burst, and we also found that many of the bursts require 2 decay components. So we use 2 decay components plus a scaling factor to model these EXO07486776 bursts that we have seen. And here we can see that we were able to constrain the burst parameters. And here in this plot, these are the eclipse bursts that occurred near the eclipse egress transition. And they're arranged such that when you go down, the burst occur farther from the eclipse egress. And we can see that the reprocessing fraction goes down as the burst occur farther from the eclipse egress. So this trend is shown here also. The x-axis is the time for the burst start from eclipse egress, and this is the dashed line which shows the eclipse egress. And as the burst occur farther from the eclipse egress, the reprocessing fraction to be observed, reprocessing fraction is observed to be lower. So this is a very interesting result, and we can imagine that if the reprocessing is happening from a parts of the accretion disk, then when the object is coming out of the eclipse, the more and more part of the reprocessing accretion disk will be visible, giving rise to increased reprocessing fraction. However, another thing that came out of this study, another similar group have done a similar analysis, and they found that the reprocessing fraction that we are getting are much higher. So some simple calculations show that even if we consider an accretion disk in such system and a perfectly reflecting accretion disk, the observed reprocessing fractions that we are getting are still much higher than what would we have for a perfectly reflecting accretion disk. So we also looked for possibilities of what other reprocessing agents can be there in the system. So at the moment, we think that accretion disk and possibly ablated wind around the companion star, where the wind density will be much higher, could be the reason behind this reprocessed eclipse burst that we are seeing. So yeah, I will very quickly pace through so that is the first part of the talk. Now this is the second part. So Indian X-ray polarimeter is a X-ray polarization measurement instrument sensitive to polarization 8 to 30 kV. Many of you may have heard about IXP, which is sensitive to energy polarization between 2 to 8 kV. And both instruments measure polarization in different energy ranges, but they are complementary to each other, because if you're looking at high energy phenomena such as accreting pulsars, the power law component doesn't stop at 8 kV. So the 8 to 30 kV is where also we see the power law component. So to understand the complete astrophysical picture of X-ray polarization, both the instrument need to work together to give a complete picture of a system. So this instrument is this instrument was launched in 1st January 2024, and it is a Thomson scattering based instrument where we have a scatterer at the center, and incoming photons are scattered off and detected by X-ray detectors surrounding this scatterer. Uh, so the principle is the polarized photons will have an anisotropic distribution in the azimuthal plane, and measuring this anisotropy will give us an estimate of polarization degree and polarization fraction. So I will not get into the details, but I'll just briefly mention the results that we have gone. So initially we looked at the crab and we were able to get the crab pulse profile. This is like getting a crab pulse profile is not that big of a deal, but for instrument like Indian X-ray polarimeter, it is, because you can see that the source count rate is around 3.5 and background count rate is 64. So these are a background dominated instrument, but we are still able, these are background dominated instrument by design, because there is the scattering efficiency of the scatterers is much lower. So even with that, we are able to get the astrophysical signal from these sources. So once that was established, that we are able to retrieve the astrophysical signal from our instrument, we moved on to measure the data from other sources. However, what we saw is our background is high enough, that was expected, but the background also shows variation in the azimuthal direction. Now, this energy range has not been explored before by any other instrument. So this kind of a background study of the background at this energy range is kind of a pathfinder, because any other future Thomson scattering polarimeter instrument would also have to encounter these problems. So in that way, learning why the Indian X-ray polarimeter background has such variabilities in the modulation is something that is of interest, and we are working on it. We looked at a lot of this modulation and its dependencies on a lot of parameters, but we have still not figured out how exactly this background depends on several factors. One thing that we think right now is the local magnetic field, the Pollux is in the low Earth equatorial orbit, and local magnetic field direction there, which determines the local trapped particle orientation. It's something that can be driving the modulation that we are seeing in the background. But that analysis is happening parallelly. Without understanding the background, we went on to another strategy of data acquisition, is alternate orbit observation, where in two satellite orbits, in one orbit we observed the astrophysical source that we wanted to observe, and the adjacent orbit we observed a blank X-ray patch of a sky near to that source. And the idea was that the overall background variations in the nearby patches of the sky will be similar, and we can subtract out the background. So with this strategy, we have so far observed crab and SCO-X1. So basically you can see the crab is here, and these are the blank patches of sky around the crab. And we observed crab and the blank patches of the sky. Yes, I'm done. And we subtract out the crab modulation and the nearby blank patch of the sky modulation, and this is what we are left with, the subtracted signal. This gives us the polarization angle estimate is around 106 degrees and polarization degree to be around 20 degrees. This right plot shows how is the subtracted background modulation difference between two blank sky regions. It shows that these are nearly flat, which is a good sign, because background subtraction itself is not introducing any other variation in the modulation curve that we're seeing. Similar observation campaign was done for SCO-X1, and SCO-X1 we're getting polarization angle to be around 8 and polarization degree to be around 3.6. So MDP is the minimum detectable polarization for an instrument. So our calculation shows that whatever the polarization degree values we are getting are much higher than the MDP. So we have a detection of polarization in these sources. So we are currently we are in the process of acquiring data for GX302 and Cygnus X1. Probably by the end of this month, those observation campaigns will also be over, and we will be looking forward to doing extrapolation measurements for these sources as well. Yeah, thank you.
Thank you so much.
Thank you.
Okay, so let's start with questions. Do we have any questions here? Ah,
I have two quick questions. One, what is the precision, what is the timing precision on polyps?
Oh, Pollux timing precision wise, these are proportional counter detectors. We have 10 microsecond precision. But it is a background dominated instrument, so doing timing analysis. Hmm.
That you're using.
Right, right. Yes. In fact, for crab, we have about months data. So we have, so as I showed the pulse profile, so we have attempted doing the pulse resolved analysis for crab, but our statistics at this moment is not very great.
And then the other question I have is about the previous part of your talk, which was that you were mentioning that the eclipses are happening during the eclipse. But like, what do you define as eclipse? Because there are some pulse profiles that are more towards the middle of the eclipse, and there is also like one source which you showed the light curve for where the eclipse is happening actually right after the inverse of the eclipse.
Okay, so how to define exactly eclipse egress? So particularly in this EXO074867, eclipse duration is itself variable. So there can be some error associated with assigning the eclipse egress exact time. We have just used the statistical errors associated with it, and we have fitted the eclipse ingress and then used the eclipse duration plus its statistical errors as to determine what will be the eclipse egress time.
The explanation of it being because of the companion ray, then we have to give to both ingress and egress. Doesn't have to be limited to just the egress, but.
It can be. It can also be because if there is any inhomogeneities in the ablated vein. And another thing is we did see another set of eclipse, as I showed here. The eclipse burst here started before the eclipse egress and continued in the out of eclipse. We did see another set of types of burst where they started before the eclipse egress and continued in eclipse period. This exponential decay component, it requires a good statistics for us to fit the curve properly. Now, when they're starting before the eclipse egress, the eclipse part has the tail which is already died down. So we don't get a good data for the eclipse part to be able to model the exponential decay there. I may have, I have some plots I can show you later, but we have such bursts, but we are not able to fit those bursts properly, so we have not analyzed them further.
Yeah, I'm still finding it.
A quick question. In the first part of your talk, you showed these beautiful results. Are there sources that you looked at where you didn't see that kind of behavior from them? Yeah, some of the X-ray binaries, right?
Yes. So in the first part, I was mainly talking about a soft X-ray component in the data, which did not change during the eclipse flare and eclipse non-flare. So,
I was wondering if you had other X-ray binaries that you didn't show in your talk, but showed something different. Or are they all the same?
So we looked at the spectral comparison, and spectral comparisons are different for different sources. But if you're talking about other X-ray binaries, when we did this survey of data, we could find such eclipse flares only in 3 systems. these 4U1737, VELAX1 and LMXBs. So I can say that for these three systems, the spectral index change, etc., is different for different systems. But I'm not sure if there are any other sources who do show eclipse variability and we still haven't. Yeah.
Okay, thank you.
I1. So you go. Okay. So that's just be later.
Sure. Yeah.
Oh, just to follow up, so have you seen, that is the first part, have you seen any non-thermal dominated spectra? Or this is not the non-thermal energy range yet? So,
We are talking about the
the
software.
first part, yeah. No, maybe, no, the hard part.
Oh, yes, I mean, you can see.
So these are not, didn't look like, non-thermal dominated, so we want just a pure power law with no emission lines.
Yeah, I can see here. Particularly 4U1737, it is eclipse flare is the spectral
Mhm.
index is negative.
Okay, but you see in all initial lines, you never have just a pure power law where the non-thermal component dominates.
Non-thermal component dominates, as in you're talking about the power law dominating.
Yeah.
So
So that the
yeah.
power part is
e-
the non-thermal electrons, I assume, right?
Right. No, I understand. I'm not sure if in general in reprocessed emission it is dominated by the lines and the
Mhm.
reprocessed like signatures of the reprocessed part. But yeah.
There will be no.
Yes.
No indication of reproduction.
Yeah.
Okay, all right. Thank you.
Thank you.
Thank you.
Thank you.